In section 3 of chapter 4, we're going to go over what is called partial fractions. Let's take a look at the objectives, where we're going to decompose a fraction that has distinct linear factors, repeated linear factors, non-repeated prime, and where Q is a prime that's repeated of a quadratic factor. Now, this seems rather technical at this point, and they are symbolizing it here, but we'll go through it in some detail step by step. So the partial fraction decomposition of a rational expression with distinct linear factors in the denominator. So this is the form. We're going to have a numerator and then distinct linear, that is only to the first power degree in the denominator. It's best to see it in action. This is the protocol we're going to follow. I'll pause here for a moment. I'm not going to read them all, but you can see as I develop these below. So, for example 1, this is the fraction. So you can see the top is linear and the bottom is actually a quadratic that has been factored. So we see the factors of it. Now, I'm going to suggest that you carefully start to write this out on your notes as we go along and show it to you here. So there's the initial example. We're now going to take the coefficient of 5, and we don't know what x is. We're going to call that a, and then put that over this, which is this part here. And we're going to take the other factor, since there are two parts to this, or I should say terms, and call that part b, and put that over this. Now, if we were going to add these together, we would have to have a common denominator, which would be these. But since we are decomposing this, we're going to reverse this process. And let's see what that looks like in the next slide. Now here, we're going to take our common denominator, which is this, and multiply the whole equation, in a sense, by this. And that's what they're showing here. So what I'd like to do is just put it here so you can follow along. And I know the screen is a little cluttered, but it's nice to have the illustration there. So this is what I have outside for the whole equation. They're just putting this on both sides. So what happens now? Well, we do a little simple algebra. Now, since we're multiplying this term by this, and there's a common denominator, all of this just cancels out here, which is what's happening here. All of this just cancels out, and this side becomes 5x minus 1. Now on this side, here the x minus 3 will cancel with this one, and we get a, and then in parentheses x plus 4, which is what we have right here. And now we're back to this again. We're going to multiply this term by this, and this time this cancels with that, and we're left with plus b and x minus 3. Okay, so again we went from this following the protocol that they're suggesting, identifying one of the factors A over it, the other factor B over it. We don't know what A and B are yet. That's what we're going to try to build up to. We are decomposing this. So hopefully you know how we got here. And they do a nice job of showing this. There's our original example. We're at this stage now. Now what we're going to do is clear parentheses by distributing. And we get this stage. Take a moment. You want to write this down. Now we want to write both sides in descending powers. Equate the coefficients of like powers of x and equate the constant terms. Now, what does that mean? Well, we have a ax and a bx. Now, this is to the first power. So, descending powers, we have to put this one first. And I don't know if you can see it, but we can factor out. Let's just write this over here. Ax plus bx. Now, if that were in parentheses, we could factor out the x. So the x would go outside, and then we're left with a plus b, and that's what they're showing here. Now, the constant terms are this one and this one, and we're just going to put those two together. Now, what was the value of our coefficient of x in this original problem? Well, that original value of x, well, the coefficient was 5. So we're going to say then that a plus b equals the 5. And what was this coefficient here? We're going to say that 4a minus 3b equals a -1, right from there. And again, throughout this, pause, look at what is illustrated, and see if you're following it step to step. Now, I wrote this out too, and I had a whole page of notes on it. So now, again, there's our original example. And we have, in a sense, a system of two equations. A plus b equals 5, and 4a minus 3b equals 1. So again, going into our toolkit, what system can we use to solve these equations? Well, let's use the addition method, where if we multiply this first equation here by a -4, and then we go to add these up, the a's will actually cancel out. So -4 times a is -4a. -4 times a positive b is a -4b. And -4 times 5 is a -20. So there's where our second line is. I would have put it out this way, but that's okay. Now, we have the second equation we just copied down, because now we're going to use that system of addition where it eliminates one of the letters. These cancel out. And we get a -7b equals a -21. So now we're going to divide both sides by a -7. And we get b is 3. Now, if we go to our first equation, which is what they're using here, and we know that b is 3, a plus 3 equals 5, we know then that a is 2. Okay, so how do we then write our final answer? Recalling what we did earlier when we said this portion was a and this portion was b. We now have a value for a, and we have a value for b. We're going to rewrite this, and remember this was the a, and this was the b. So our a is 2 now, and our b is 3. Now, what I'm going to do is go to the whiteboard and prove that this is in fact the answer. And before I go to the whiteboard, I just want you to see what I'm copying down. That is, this is going to be equal to this. Okay, let's go to the whiteboard. Now, in order to add fractions with unlike denominators, we must first have a common denominator. So what is our common denominator here? Well, it's a combination of these two. So our common denominator is going to be x minus 3 and x plus 4. Now, we are allowed, and I'll change colors here to show you what I'm doing, to multiply each of these fractions by a 1. And that doesn't change the value of the fractions. It just makes them an equivalent fraction with a new denominator. Well, what form of 1 would I multiply this one by to get this denominator? Well, it's missing this part. So I'm going to use the form of 1 of x plus 4 over x plus 4. And would you agree to that? I'm not changing the value. I'm just multiplying this fraction by 1. Now this one, again, I'm going to multiply it by 1 so that it becomes this denominator. Well, this one's going to be x minus 3, x minus 3. And now both fractions have the same denominator. But I need to collect like terms on top here. So let's do that. So I get 2x plus 8. And remember there's a plus here. This becomes plus 3 minus 9. I think you could all agree with that. Now, what does my numerator become? Well, this is 3x. I forgot to put the x. 2x plus 3x is 5x. And positive 8 and a negative 9 give me a negative 1. Oh, I have gotten this over my common denominator, x minus 3 and x plus 4. Wow. So what we have just done is we have decomposed this into what it was originally, and that's the skill we're working on. And going now back to our regular board, we see that in fact, this is our answer illustrating decomposition. So far in this series of flipped lessons, 14 minutes is the longest I've spent on just one example. Again, these are rather challenging. And as we look at our next example, the partial fractions decomposition of repeated linear factors. All right, let's take a look at this. It's similar, but different. So there is our basic example. And we're going to take our numerator, though, and since this is to the, there's one power here, third power, we need 3 values. We're going to separate this into an a that we don't know over the x plus b over the x minus 1, because that would be one of the factors. And then since this is the third power, we need an x minus 1 to the second as well. plus c. Now, the next step is the very same as what we did earlier. We're going to multiply these equations by the lowest common denominator. Each term, get rid of our denominators, put it all up into the numerator. You're going to see that on the next slide. And again, I copied this down, and you should too, and pause as is needed. Okay, so there is our lowest common denominator that we're multiplying this whole equation by. They're showing it like so in two parts. And now let's do the multiplication. Well, on this side, notice that these just cancel out. And we're left with, this is sort of a pattern that we're building now, x plus 2. And now it's going to be a. The x's cancel out, and we get a, and then in parentheses, x minus 1, the quantity squared. Now, for the next term, one of these cancels from this, but we're still left with one. So we get b times the x here, and then times one of the x minus 1. Now, the nice thing about this last term is that the x minus 1, the quantity squares, cancel out here, and you're only left with the cx. So this is where we are. We'll go to the next slide. And following a similar pattern from our first, again, there's our original example. There's where we've gotten rid of all our denominators. Now, we have to get rid of this parenthesis here. This is x minus 1, the quantity squared. So binomial squared, we're going to expand that. And we square the first term. That's x squared. We multiply these two terms together. We get a negative 1x. Double it. That gives us our middle term, a negative 2x. And then we square a negative 1, which gives us a positive 1. So you may recall this is a perfect square trinomial that came from squaring this binomial. Now, next step, of course, is we're going to take this and then distribute that a, and we get this stage, but we're getting ahead of ourselves here a little. Now, multiplying this x times this, we get x squared as we distribute, minus a negative 1x, if you want to put the 1 there. By convention, we don't write it. And then this is just cx. Now, we've gotten rid of our parentheses. By distributing that, we now have this line. So what do you think our next step is? Well, we're going to get all our terms together. So let's do that one before we see it. Now we've got a x squared, and we've got a plus b x squared that I'm just going to put in parentheses. Then our x terms. So we have a, in parentheses, negative ax right there, minus bx right there, and then a plus cx right there. And then what are we left with? We still have a plus a out here. All right, now what we want to do is factor out the x squares here. So this then becomes in parentheses a plus b x squared plus a negative a negative b, a plus c, x, and then we have an plus a. So staying on the whiteboard for a moment and then getting back to our regular screen and then clearing this up, you see this is what we got. But now in this next step, it's write both sides in descending powers equal the coefficients of the like powers of x and equate the constant terms. Now out here, in a sense, there may have been an x there or something like that. Maybe not there though. I don't want to put it there because that would make this a 0. But the sum of this, if we add it together, is the constant of x squared, which is a 0 in this case. So that makes the sum of our a and b here, since there is no value there up there for this, a 0. That one's a little tricky. This one's a little easier to see. If we take this portion here, what was our x value? Well, we see it very well there was a 1. So this portion equals 1. And now the a is the x, the coefficient of this term, which is 2. So these are our three equations. Let me pause. I'll give it another shot. Since this is a and b and there is no value for it up here, it's going to be a 0. And then the others, I think, went very well. This is our x value, which is a 1. And then this is the a value, which is a 2. So now what do we do? Well, it gets a little more complicated, but we now have 3 linear equations that we want to solve using, again, going into our toolkit. What do we do? Well, we know that a is equal to 2 here. So a plus b is going to be, let's just do that here. A is 2. We don't know what b is. We just transpose that 2 over where it becomes a negative 2. So we have a equals 2, b equals a negative 2. So how do we find what c is? Well, we're going to take these two values, put it into this equation, which is what they're doing here very carefully. So there's your 2, there's your negative 2. We don't know what the c is, so this is negative 4. This is a positive 2. This arithmetically becomes a negative 2, which we're going to transpose, becomes a positive 2 on that side. And here c is 3. So we now have our 3 values, a, b, and c. But how do we write the decomposition? So if you recall, when we set this up initially, we had this, and then we said a over this, b over this, c over this. So now when we put these values in, a is 2, b was a negative 2. We're putting the negative on the line of the division bars here. It could have been like this. This could have been a plus negative 2, but I see they're putting it this way. So let's go along with that. And then plus 3. Now, again, what's our common denominator here? Well, it's all of this. And if we did what we did earlier, this would then become this. Again, this is the multiplying and then adding unlike fractions. This is the decomposition of it, and it's challenging. Now, in our third example, we're looking at the partial fraction decomposition of a rational expression with prime, non-repeating quadratic factors in the denominator. Now, as we look at the setup for this is a little different here. It's ax plus b, which is the linear numerator, and then, of course, the quadratic factor in the denominator. So in step 1 of example 3, we're going to set up the partial fraction decomposition with the unknown constants. So there's our initial example, and we're going to say a over this, and then bx plus c over this. And you might say, well, what's our next step? Well, we're going to get rid of all our denominators here by multiplying both sides and each term by our common denominator. And we see that in the next slide here. And they're doing this the way I showed this initially, putting the common factors outside here, and then putting a bracket by the whole equation. So what happens here? Well, this is the easy part. Since this is the common denominator, all of this cancels with this, and you're just left with the left side of the equation. Now we're going to take our a and multiply it by this, but we can cancel out the x minus, or the x plus 3. So we're left now with a times this, which is what is shown right here. Now, notice the quadratic cancels out now, and then we're going to put in parentheses bx plus c times x plus 3. Again, there's a lot of algebra going on here. Now in step 3, this side pretty much stays the same, but we're going to distribute now the a, and that gives us this line. But now we have to FOIL these two binomials. So bx times x is bx squared. Bx times 3 is 3bx. Our inners is a separate term, so that would be plus cx, which is, they're writing it out here. And then c times 3 is 3c. Wanted to show you where all that is coming from. Now we want to collect our variables in groups, as we've done before. So we're going to go ax squared plus bx squared, and put that in parentheses, plus ax plus bx, 3bx, plus cx in parentheses. And then we get a plus 2a and a plus 3c. And this side stays the same. Now, what do you think our next step is? Well, we're going to factor out the x's here, x squares first, and we get a plus b x squared plus a minus 3b plus c with an x and this was meant to be here 2a, I guess, yes. Sorry about that. And then this is plus 2a plus 3c. And I can put these in parentheses here. And now let's see what it looks like. So there's my factoring out the x squares, factoring out the x, and then these values, we're just collecting them and putting them in parentheses. So as part of our decomposition now, our coefficient of x squared, which was our a term, was 8. So a plus b is 8. That would be one equation. And then this term, 12x, which was our b term here, a plus 3b plus c is going to equal this. That was our x value, 12, coefficient of x. And then to the 0 power, the degree, what's left was 2a plus 3c equals a negative 20. So again, following that same pattern that we've seen so far. There's our composition, and on other paper I told you I wrote each of these out. These are our three equations. Here we have three, in a sense, variables. What technique would you use? Well, now this is a little misleading as the way they set this up, but I'm going to take this first equation, a plus b. Now there is no c term, so I'm going to put 0 there, equals 8. I'm just rewriting this term, these terms. And now I want one of the letters to cancel out. So if I multiply everything in this equation by, let's say, a negative 3, I get a negative 3a, there it is, a negative 3b, which is what they have here, and the 0, nothing there, and then negative 3 times 8 is a negative 24. I get this. And again, I don't know why they didn't line them up nicely, but here what happens is your b's cancel out, and you get a negative 3a and a positive 1a, leave you with a negative 2a plus c equals a negative 12. Now you have an equation with just two variables, and you see we can use this third equation here, which just has the letters a and c in it. And if we multiply, or actually just put one on top of another, because here a negative 2a will cancel out. That's what this equation is here. These cancel out now. We get 4c equals negative 32. Our c equals a negative 8. And what will our b be? Well, we'll see that on the next slide here. Wanted you to see where it came from. So, with the value of c being a negative 8, we can go into this equation and solve for a. And we end up with a equaling 2. So c is negative 8, a is 2, and now we can go to the first equation with a is 2, b is going to be 6. So what will our decomposition look like? Recalling where we started, or the top of your page, or wherever, we had that this was A, this was B, and this was C. So our constant here is going to be 2. A we said was 2, so that goes 2, and then plus our B value was 6, and then our X, 6X, and then minus 8. And there we have it. Wow. Again, you may want to pause, reflect on what was going on, and check it out again, step by step. These are challenging. In the last example that they're giving us, the partial fraction decomposition of a radical expression with a prime repeated quadratic factor in the denominator. So we need to look at the setup of this. So there's our original. And then notice that this is to the first power. This is to the second. This is to the third, and so on. Fortunately, we don't have to go any further than this. This is all we're going to deal with. But I wanted you to see where this came from. So there's A sub 1, B sub 1, and then new letters, which we will call in our next slide a C and a D. And now let's take a look at it. So there's the example you are to write down. That's the initial, which we could put right here. And then using that format we saw in the previous slide, there's your binomial. And in a sense, this is to the first power, which we therefore don't need parentheses. But now this is the second power. And there's our A plus B and our C plus D. And again, following what we've done before, you might say, what are we going to do next? Well, we're going to multiply all of this by our lowest common denominator, which is x squared plus 1, the quantity squared. And we'll see that in the next slide. Now, they've set it up so we're using our lowest common denominator there and on the other side. Instead of putting it all in one, they've put it in two parts. So what happens? Well, nicely, these just cancel out. And on the left, we end up with this. Now, as we multiply through, this will cancel with one of these. So you have this and one of these that you'll have to multiply through. But now this cancels completely with this, and you're just left with that. So you probably see where we're going with this. We're going to FOIL this, and we'll see that in our next slide. So foiling this, we get ax to the third. Our outers are a 1 that we don't write, ax there. Our inners, a bx squared. And our last, just a plus b. And we have this. And you might say, well, what's next? Well, as we've done before, we're going to group these into ax to the third. We don't have anything that will go with this, so this is going to be plus b x squared there. Now here we have an ax and a cx. that we're now going to put as A plus C X. And then we have a B plus D that we can group together. So that's where we are. Let's go to our next slide. Matching this up now with our constants. Here we have, to the third power, we have a 2. Now, there is no 0x to the second power. So our b value here would be a 0. Our a value is going to be a 2. And then our a plus c value is going to be a 1 here. And then our b plus d is going to be a 3. So take a moment, pause, go over what I've just shown you to see how this ties in. This is the easiest of finding the various values for our grouping. We know A is 2. We know B is 0. So, and we know that A plus C is 1. And we know that A is 2. So our C value is going to be a -1. And we know our B value is 0. So 0 plus D is 3. D is 3. So our A is 2. Our B is 0. Our C is -1. And our D is 3. Now, putting this into its final form, now winding this up, again, if you think of this trinomial to the third degree, there is a placeholder, has no value, but this x to the second is a 0. So then substituting our values, A, B, C, and D, into this, it's going to be this, and our coefficient of x to the third is 2, and then plus, keeping in mind that the sequence of this was 1, this was 2. Our coefficient of x here, since there is no b value, well, yes, no b value, that would be like plus 0. We only write the 2. And then we go to this constant, which is c, a -1. So a -1, that they're not writing the 1. That's the proper form. And then our d value is 3. So this is the answer. Again, these are, for some of you, I'm sure, a challenge because lots of skill involved and following the protocol of decomposition. All right, we'll wrap this up.